Okay, student notes 2.2. This is graphing general sinusoidal sine and cosine graphs. We saw in spaghetti trig what the sine and cosine parent functions look like. Now we're going to take it a little bit deeper and look at the transformations. And so just to define a few words before we begin, amplitude. You've probably heard this and have a general idea of what this word means. But when we're talking about sinusoidal graphs, the amplitude of the sinusoid is the distance from the sinusoidal axis to the high point or low point on the graph. Okay, so it's basically the height of the wave from the middle to the top or from the middle to the bottom. And we're going to see what that looks like in this first example if you are unclear on what amplitude is. Okay, cycle. Again, this is another word you should be used to, but in this context, a cycle of a periodic function, periodic meaning sinusoidal, it's a repeating pattern. A cycle of a periodic function is a portion of the graph from one point on the graph to the point at which the graph starts repeating itself. Okay, so we saw in spaghetti trig that the sine and cosine graphs look like a wave, and the cycle of the parent function was 2 pi. And we'll talk more about that cycle can change, and that will change something else called the frequency. Okay, the period of a trigonometric function is the number of degrees or radians that it takes to complete one cycle. So again, for the parent function, we saw that this period is 2 pi. That was how long one cycle was, but that can change. It can be horizontally compressed or stretched. Okay, so we're going to graph y equals 4 sine theta by filling in the chart. All right, now if you know your OIO chart, this is going to be super easy. So 0 degrees, if x and x here is our theta. So if theta is 0 degrees, what's 4 times sine of 0? Well, if you remember that sine of 0 is 0, or you remember it from your OIO chart, multiplying it by 4, we'll just keep that right at 0. All right, what's sine of 90? It's 1. So we'd multiply that by 4, we get 4. Okay, 180. Sine of 180 is 0. So multiplying by 4 doesn't really change it, keeps it right at 0. And sine of 270, according to the OIO chart, is negative 1. So multiply that by 4, we get negative 4. Okay, and all these values you could get on your calculator, or you could also get them by plugging this into y equals and using the table on your calculator. You could, if you did this by hand, which is what we're doing, you'd have to use the OIO chart. If you have questions about how I'm coming up with these values so quickly, please come to tutoring, ask me questions. All right, 360 degrees takes us right back to 0. So it may look that the pattern started repeating itself right here at 180, but that's not true. It didn't really start repeating itself till 360, which makes sense because 360 degrees is 2 pi. All right, let's plot these points. And so our independent axis here is the x, that is our theta, our degrees, and our dependent axis here is these y values represented by 4 sine theta. Okay, so let's plot 0, 0, 94, 180, 0, 270, negative 4, and 360, 0. So if you weren't quite sure the pattern was going to start repeating itself at this point, hopefully it's a little bit clearer now. This looks like what we did when we had spaghetti trig. And if you put a little curve into it, you can see that this is one cycle. Okay, so the amplitude, this is back to this word that you're probably not quite comfortable with yet. When I say sinusoidal axis, by the way, I mean the middle of the graph. So I'm putting a dashed line here. This is not an asymptote, but it is not something that is part of the graph. It's just there to kind of help us see. Both in the parent function and this problem, the sinusoidal axis is on the x-axis. We can see from that sinusoidal axis up to the highest point is 4 units. Okay, so that's 4 right there. Same thing if I look over here at 270 degrees. From the middle, the sinusoidal axis, to the lowest point, that's 4. That means that the amplitude of y equals 4 sine theta is 4. So you can kind of make a conjecture as to what would happen if we changed this 4 to a different number. All right, one other thing to point out before we move on to the next example is that notice that this was a sine problem, okay? And we started at the origin, just like how the parent function of sine theta we noticed from spaghetti trig started. All right, let's go to the next example. Okay, here we have a cosine and we have a different number. We have a 3. All right, so if you want to go ahead and try to guess what the amplitude is, you could. We'll see if you're right. So again, I'm going to use the OIO chart, and remember here that pi over 2 is just like 90, pi is just like 180. You don't have to convert all of these to degrees, and in fact this is a nuisance once you're really comfortable with radians. But I just want to make sure everybody's clear. These are the exact same independent values we had last time. So in using the OIO chart, make sure you're looking in the cosine column, because cosine is 0. It's not 0, it's 1. When I multiply that by 3, I get 3. Okay, cosine of pi over 2 or 90 is 0. Again, you multiply that by 3, you get 0. And on goes the chart. -3, 0, and 3. And right here is where the pattern starts to repeat itself. Okay, so let's plot these points. 0, 3. Pi over 2, 0. Pi, -3. 3 pi over 2, 0. And 2 pi, 3. And again, we have one cycle. Now we had a different starting place. We didn't start on the sinusoidal axis. We started at a high point, which is typical of cosine. We saw that with spaghetti trig and the parent function for cosine. Okay, again, I'm going to go ahead and put in the sinusoidal axis just to make sure it's really clear here. And I can see that from the middle to the low is 3, and from the middle to the high is 3. And it wouldn't matter which one I took. If I went over here, it would still be 3, because this pattern is sinusoidal, which means that it goes up, it comes back down, but it reaches relatively the exact same highs and lows. Now, it looks kind of over here that I went up a little too high. That was just user, not being exactly accurate. This is at 3. Okay, so the amplitude is 3. If you guessed it right, give yourself a pat on the back. Again, notice that the period here is 2 pi or 360 degrees, which is the same as the parent function. All right, so in general, the graph of y equals a sine theta has an amplitude of a. All right, and it's nice that we have an a there, and amplitude starts with a. It's kind of nice. Help us remember that. Okay, this is a vertical stretch for both of these problems, just relating it back to what we've already learned in Algebra 2. Now, it could be a compression. Okay, I want you to think for a second about what type of values you would have if it was a compression. That's right. If a is greater than 1, we'd have a vertical stretch. If a is less than 1, we'd have a compression. You don't see vertical compressions too much, but it definitely could happen, and you will see it from time to time. Usually, though, a is going to be an integer larger than 1. Okay, let's move on to the next part. Okay, on the next part, you notice we have a number again, but it's not being multiplied to the entire trig function. It's just being multiplied to the angle. And so thinking back to transformations, this is not going to be a vertical stretch or compression. This is going to be a horizontal stretch or compression. This is going to change our period, the cycle, and all of that in something called frequency. All right, let's just start, though, by filling in the table. Don't get too ahead of ourselves just yet. And so there's 3 columns here, and that's just to kind of help you do this more without a calculator, but using your OIO chart. So if 3 theta is 0, what would just theta be if you divide by 3? Okay, so that would still be 0. And what you're doing here is you're finding sine of 3 theta, or sine of 0. Okay, that's a 0 as well. So this gives me my x and my y. The 3 theta here is just to kind of help out. So it makes a little bit more sense on the next one. So 3 theta is equal to 90 degrees. They're giving the 90 degrees. What would that make just theta then be? You would have to divide by 3. That would give me 30 degrees. So now my x value is 30. However, when I'm trying to find sine of 3 theta, I'm taking sine of 90. And sine of 90, using our OIO chart, is 1. All right, but the point that I'm going to plot is 30 degrees and 1. All right, let me put a degrees here as well. All right, so again, 180. If I divide that by 3, I'll get just theta, or my x, and that is 60 degrees. Okay, but when I'm taking sine of 3 theta, I'm really taking sine of 180, which is 0. And I can see these numbers, I can see the pattern in both columns. Okay, so for 270 degrees, x would be 90 degrees, and sine of 270 is negative 1. 360 divided by 3 is 120 degrees, and sine of 360 degrees would be back at 0. Okay, so 0 degrees to 360 degrees, the pattern is repeating, but the x, it starts repeating at 120 degrees. So again, this is probably easier to see it as a visual, so let's plot these points. And when we're plotting them, it's going to be these points. So even go ahead and put your parentheses in. That 3 theta column was just there to kind of help us along and figure out what values to start with. So I have 0, 0, 30, 1, 60, 0, 90, negative 1, and 120, 0. And you can see that this amplitude is 1, like the parent function. Amplitude is what we did on examples 1 and 2. From the sinusoidal axis to the top or to the bottom is 1. Okay, but something else changed here. The pattern started repeating itself. Instead of 360 degrees, it started repeating itself at 120 degrees, which I already mentioned, but we can see it now on the graph. Okay, from here to here is 1 cycle. So the cycle became 1/3 what it was. Okay, and you can think of, oh, it's 1/3 and not 3 times, because on a horizontal change, it's always opposite of what you think. So you think we were multiplying the period by 3, but really we're dividing it. Okay, and so let's answer the next part here. There's a critical high, low, or middle point every so many units. Okay, so these are these points that I plotted. All right, so let's think. From one to the next is every 30 degrees. And these are your tick marks, or your hash marks. Okay, and that's what we're going to call a critical point. Okay, these are your tick marks, and we can see that they're 30 degrees. All right. One thing I want to point out before we move along is that although in a particular cycle there are 5 hash marks, it's really broken up into 4 sections. Okay, so a way you could find how far apart your critical points are is to divide your period by 3. Okay, so let's write this down. Critical points, that distance is going to be the period. I think I said divide by 3, I meant divide by 4. The period divided by 4. And the reason, it may seem like random why they picked 4, but think back to a circle. A circle has how many quadrants? 4 quadrants. So the sinusoid, whether it's sine or cosine, is going to have 4 parts, 1 for each quadrant, basically. Okay? All right, let's look at the next example, and then we'll kind of develop a rule here. Okay, problem number 4. Graph y equals cosine 2 theta by filling in the chart, and we're going to label the x-axis. Notice that these tick marks are not labeled, and we need to do that. All right, I'm going to do this one a little bit different than last time, just to make sure that everybody is understanding how we're getting our theta here. It's that we're dividing each time by this number 2. Let's go ahead and fill in this whole column, and then we'll go back and fill in the y column. So if I divide 0 by 2, get 0. Divide by pi over 2 by 2, get pi over 4. Divide pi by 2, that's easy, pi over 2. 3 pi over 2 divided by 2 would be 3 pi over 4. And 2 pi divided by 2 would be pi. Okay, so these are my tick marks, and I'm going to go ahead and make one at 0. That will become more important as we get into more complicated type problems. You want to make sure you know where your tick marks are and label them correctly. Alright, so now let's go through and fill in the third column. Now notice again I'm doing cosine of 2 theta, so you are going to use the first column. You're not even looking at the middle column when you're finding cosine of 2 theta. Use the OIO chart. So cosine is 0, that's 1. Cosine of 90, or pi over 2, that's 0. And then you just keep using the chart as you go through. So notice it shortened the period. Okay, the period in the beginning was 2 pi, but the period now is going to be pi. Let's look at this visually. Okay, I'm going to switch colors here just to make it stand out. So if we plot our points, we get 0, 1, pi over 4, comma, 0, pi over 2, negative 1, 3 pi over 4, 0, and pi 1. These are all points. Again, we have x, we have y, we just plot the points. And then when you're connecting these dots, it doesn't have to be perfect, but you want to make it look as much like a sine or cosine graph as you've seen. Okay? So from high point to high point, this is one cycle. That is the period. So in this case, the period is pi. Okay, so the period of y equals cosine 2 theta is pi. Okay, there is a critical point every, well, I can see right here. I'm going to use CP for critical point. I go 0 to pi over 4. And then if I kept adding pi over 4, I'd have to do a little bit of fraction work, but it's not too bad. I could see how I get from critical point to critical point. And this is how you're going to do this in the future. Okay, so critical point every pi over 4 units. Alright, so again, this is a horizontal compression problem. Okay, so when we're generalizing the period of y equals cosine b theta, let's think about that the period in the beginning of our parent function was 2 pi. By putting a 2 right here, I halved the period. Okay? So I divided by 2. Let's see if that was a rule for the first one. This isn't as obvious, but we can develop it. So again, in degrees, it was 360 for the parent function for sine, but when I put a 3 in front of the theta, I had to essentially third, or cut in third, all of the tick marks, or hash marks, and the cycle as well. Okay, so the period I divided by 3. So what we're doing is we're dividing this by b, okay? And so this could be either 360 over b if you were wanting to be in degrees, or this would be 2 pi over b if you were in radians. Okay, so b itself is not the period. You use b to find the period. B is something else called the frequency. And I'm going to briefly explain what that means with this example we did just this last example. So if 2 is the frequency, it means that there are 2 cycles where there once was only 1. So if I were to continue graphing this, how many cycles would I have if I graphed it all the way out to 2 pi? I would have 2 cycles. That's what frequency means. It means the number of. Okay, if we look at this one, there's 1 cycle in 120 degrees. There would have been 3 cycles if I had gone all the way out to 360. Okay, so again, this is a horizontal compression. It could technically be a stretch if our b was a number less than 1. Alright, so we already saw that to go from period to critical point, we would divide by 4. So let's think of what this would be in general. If I divided 360 over b by 4, I'm really just needing to divide 360, so that'd be 90 over b. And then if I divide 2 pi over b by 4, that's going to be pi over 2b. You're really not going to use that. In fact, it's not wrong, but I'm going to kind of put a little slash through it in green. What you're going to do to find the critical points, the easiest way is to just take whatever the period is and then divide that by 4. Okay, so let's practice what we've learned. I'm going to switch back to red here. I like red. To sketch 2 complete cycles of each graph, clearly label all critical points, high, low, and middle points. The y-axis tick marks are not necessarily 1 unit apart. Alright, so we only know about 2 things. We know about amplitude, we know about period. So remember, amplitude is this number right here. So let's mark this down. I'm going to call it amp. I'm going to call it 6. So that means from the middle of the graph, which right now we're still dealing with the middle of the graph as the x-axis. If I go up 6, down 6. So I'm going to put in an extra little tick mark here. I'm going to let that be 6. And down here would be -6. And you could mark this as 3 and -3. That's not entirely necessary, but it would kind of help you see what's going on. All right, now let's find the period. So again, the period is not 5, all right, but that is our frequency. But I would take my number of degrees in my parent function, which would be 360, and I'm going to divide by 5, and that gives me 72 degrees. This is my new period. Okay, so if I want to sketch 2 complete cycles, then I'm going to have to go at least twice this. All right, the other way that I'm going to show you to make sure you've sketched 2 complete cycles is to find the distance between the critical points. So remember, you take the period, whatever the period is, which in this case is 72, you're going to divide that by 4, because there are 4 parts, and that equals 18 degrees. Okay, we're going to start at 0, and we're going to go 18 degrees, and you do need to write all of these out. So 18 degrees, 36 degrees, 54 degrees, 72 degrees, that's 1 cycle. Now we got to go more, so 90 degrees. You should be able to do this without a calculator. Obviously it would be easier with, but these are not calculations that you have to have a calculator to do. Now if you have plotted 9 points, then you should have 2 complete cycles. So 1, 2, 3, 4, 5, 6, 7, 8, 9. You can definitely go to the left and do something like this as well. And we are going to get to where we're always doing this soon. Alright. Once you find the amplitude and the period and you mark your tick marks, that's really actually the hardest part of this, because the rest is figuring out where to make your first tick mark. And that's where you actually look on whether you're dealing with a sine or a cosine. Now I'm dealing with a cosine, and if you remember about the parent function, it starts at a high point or a peak. Or you could think of, what is cosine of 0? It's 1, not 0. So we don't start in the middle, we're going to start at the peak. Alright, you can definitely plug in a number just to make sure, like 0, to make sure that you're doing this correctly, but we're going to start at a high point. And we're going to go to the middle in the sinusoidal axis, and then we're going to go to a low point. Then we're going to go to the middle. Then we're going to go to a high point. It's going to repeat this pattern. So once you got your tick marks, you just got to make sure your first point's right, and you're good. And if I want to go to the left, I'm doing an extra one here just to kind of prove a point. My sinusoidal axis is on the x-axis. It will not always be so, but for right now that's all we know. And then you're just kind of filling in what you don't know. Okay, so we can see here that this is 2 cycles. Some things that we're going to talk about in the future. Make sure that you know how to find domain and range of this. Domain is easy, okay, because that's going to be all real numbers. There's just a little bit of review. Range, that's not too bad either. It's -6 to 6. Again, though, I can shift this graph up, left, down, right. I can flip it over. I can do the other transformations. We'll get to that really soon. This is all we got to do for now. Okay. So let's try a new one. Okay, again, amplitude is 8, and it's a good habit to get used to writing this at the top of your page. The period. Now this is in radians, so I got to do 2 pi divided by 1/2. And please, please be careful about this. This is not pi. We're not dividing by 2. We're dividing by 1/2, which is 4 pi. And so then you would find out, well, how far apart are my critical points? Take their period and divide that by 4. So I get pi. Now this makes this really nice, because my up and down, my vertical tick marks are going to be 8 and -8. Alright, we knew that. But now I can just say pi, 2 pi. This is not always going to be so easy. Sometimes you're going to have to deal with some fractions here when you're dealing with radians. And if I go all the way out to 8 pi, then I know that I've done 2 cycles. Okay, again, look at whether you're dealing with sine or cosine to know where to put your first tick mark. So for 0, okay, sine, like the parent function, starts on the sinusoidal axis and then it's increasing. If you weren't quite sure where these 2 points were, just plug in 0 in for theta or plug in pi in for theta and do that exact value. You should be able to do that without a calculator. And follow the pattern. It just goes from the middle to the high to the middle to the low to the middle to the high, and then it repeats itself. This is why these are called periodic functions, because they repeat. And you could check any of these points that you wanted to. Again, domain and range, pretty easy to find. We'll practice that more in the future. Okay, so now let's talk about something a little bit different. Consider the parent function y equals sine theta. Well, we know what that looks like. Describe the transformation of what's going on here. Now this is just like your first after party where I was asking you about transformations. Okay, so let's see what you remember. If I add 5 to the entire function, that's going to be a vertical shift up 5. I'm going to abbreviate here. What about -3 in place of 5? Right, that's going to be the same thing, vertical shift, but it's going to be down 3 in this case. What about plus 50 degrees? Notice it's on the inside of the parentheses, so we're changing our x value or our theta value. This is going to be a horizontal shift. Which direction? Remember, this is a little tricky. All right, this is going to be left 50 degrees. Same thing here, but right. In this case, we're dealing with radians. So this is right 3 pi over 4. So you may be thinking, well, why am I throwing all this in? Now, if we took any of our examples we just did, and I put something like a 2 plus in front of it, well, you just have this shifted up 2. Or in parentheses, if I had a minus, in this case, it'd probably be something like minus 2 pi. Well, then it would be shifted to the right 2 pi, and that's how you would graph more complicated graphs. The last transformation we need to talk about are reflections. Okay, so what I'm going to do is I'm going to graph the parent function in blue. And it's just going to be a very quick sketch. So remember, our sine parent function looks like this. Okay, it goes right through 0, 0. If I put a negative in front of sine of theta, this is a vertical shift. And what that will do is I will still start at 0, 0. But instead of going up, I'm going to go down. So notice that all the points on the sinusoidal axis don't change. It's just that the high points become low points and the low points become high points. Okay, so we're going to call this a vertical reflection. This is a reflection across the x-axis. So let's write that below here, across x-axis. Now, if our sinusoidal axis is moved up or down, it won't be across the x-axis, it'll be across the sinusoidal axis. Alright, let's try to look at what cosine looks like. Okay, so again, I'm going to graph the parent function. Remember, cosine of 0 is 1, so cosine starts at a peak and looks something like this. These are just rough sketches. All the points on the sinusoidal axis, they don't change, okay, because you reflect something over x-axis, and if it's on the axis, it won't move. But the high points become low points, and its reflection looks very similar to what happens with sine. So it's the same thing that's going on here, a vertical reflection across the x-axis. What you need to remember when you're graphing cosine is you don't start at a high point, you start at a low point. Okay, the parent function starts at a high point. If you have a negative right there, okay, and basically this will mean that your amplitude is negative, then you are going to start at a low point. And we're going to practice this in examples, but always be thinking back to the good transformations that you learned last year in Algebra 2, and that will help you with this. Okay, so in summary, Describe the effects of A, B, C, and D for y equals C plus A sine B theta minus D. Now, we already know what A is, all right? It's the amplitude. Remember that this is like a vertical stretch, okay? We could write that out here. And it could be a compression as well. We're going to call this, though, amplitude. We'll abbreviate. All right, B. B is not the period, but it tells you what the period is. It tells you that the period could be 360 over B, or it could be 2 pi over B. It just depends on which, whether you're in degrees or radians. And this is a horizontal stretch or compression, depending on the number. Okay? C, we didn't call it C, but we saw that this was a vertical shift. Okay? Remember that it's going to go up if C is positive, and it's going to be down if C is negative. Okay, D is going to be a horizontal shift. And that, again, we have theta minus D. If D is positive, that's going to be theta minus a number. That's to the right. Okay, so it's actually right if it's positive. Okay, but what that would look like would be theta minus, 20 degrees or something. Now, if D was actually negative, okay, minus a negative would really be plus, so what this would look like would be theta plus, we'll just call 75 degrees, okay, that's going to be to the left. So it's the same thing that you've realized. I don't want you to get confused just because there's a minus here. If it's theta minus something, it's to the right, okay, but that will translate to actually a positive D. All right, if it's theta plus something, we're to the left. So we're not using different rules. It's the same thing we've seen before.